Good evening, and welcome back to SleepWise. Tonight, we begin beside a cliff. It rises in the half-light like an ancient library, layer upon layer of stone pressed together by time, each band a page, each fossil a sentence written before forests, before birds, before footsteps on land. A geologist traces one narrow line with a gloved hand. Below it, the stone is crowded with shells, fragments of coral, and armored creatures that once moved across shallow seas. Above it, many of those shapes are gone. The line itself is only a few centimeters thick. Yet it divides two different worlds. Earth is about 4.5 billion years old, and life has occupied it for most of that span. Over time, life diversified into reefs, forests, insects, fishes, reptiles, mammals, and countless forms that left no descendants. More than 99% of all species that have ever existed are now extinct. Most disappeared gradually, one lineage at a time, as climate shifted, habitats changed, or reproduction failed. A mass extinction is different. It is a geologically brief interval in which extinction rises far above the normal rate and spreads across many branches of life. Oceans empty, reefs collapse. Food webs unravel. Creatures that endured for millions of years vanish within a fraction of that time. Geologically brief does not always mean sudden to us. Some crises unfolded over tens of thousands or even hundreds of thousands of years. That is longer than recorded human history, yet to Earth it is almost an instant. Scientists recognize 5 severe crises in the fossil record, often called the Big Five. They occurred at the ends of the Ordovician, Devonian, Permian, Triassic, and Cretaceous periods. One was linked to deep cooling and falling seas. Several unfolded beside enormous volcanic eruptions and changes in climate and ocean chemistry. The most famous followed an asteroid impact, but extinction is only half of the story. Above each dark boundary in the rocks, life continues, not unchanged and never restored exactly as it was, but reorganized. Survivors spread into emptied habitats. Small, overlooked creatures inherit landscapes once ruled by giants. New reefs rise where older ones failed, and new forests appear beneath unfamiliar skies. The history of life is not a smooth climb toward the present. It is a long sequence of flourishing, interruption, endurance, and renewal. Tonight, we will cross 5 thresholds in deep time. We will enter lost worlds while they are still alive, notice the first signs of change, and follow clues preserved in stone. We will ask what happened, why it happened, and which quiet advantages allowed some forms of life to pass through the darkness. For now, remain beside the cliff. The evening air moves gently across its surface. The ancient line waits beneath the geologist's hand, thin enough to overlook, yet vast enough to contain the ending of a world. The stone beneath the geologist's hand does not speak in words, it speaks in absences. A shell appears in one layer, then never again. A reef flourishes for millions of years, then gives way to dark mud. Tiny grains of volcanic ash settle across an ancient seabed and later become a clock, their radioactive elements changing at a steady rate that allows scientists to estimate when the layer formed. Elsewhere, a thin band of unusual metal, a sudden shift in carbon, or a change in the chemistry of fossil teeth reveals that the air and oceans were becoming unfamiliar. This is how Earth's great extinctions are reconstructed, not from a single perfect record, but from thousands of scattered clues. Fossils provide the most visible evidence. Paleontologists compare which species occur below a boundary and which survive above it. Yet fossilization is rare. Most organisms decay, are eaten, or disappear without leaving a trace. Hard shells and bones preserve more readily than soft bodies. Shallow seas leave richer records than mountains or forests, where erosion may remove entire chapters. A gap in the rocks may represent a missing afternoon or several million years. So the first task is to ask whether a disappearance was real. Scientists test the same pattern across many locations. If a group vanishes from one coastline, it may simply have migrated. If it disappears at nearly the same time from rocks on several continents, the signal becomes harder to dismiss. They then examine the sediment around it, grains shaped by storms, minerals formed without oxygen, pollen from damaged forests, soot from fire, or droplets of once molten rock thrown high into the atmosphere. The dates must also agree. Layers of ash can be measured with radiometric techniques, while reversals in Earth's magnetic field and recurring changes in the planet's orbit help match distant sequences. Together, these methods turn separate cliffs, quarries, and drill cores into pieces of one enormous timeline. Even then, certainty comes slowly. A mass extinction may have a trigger, but the trigger can set off a chain. Volcanic eruptions may release gases which alter climate, which change ocean circulation, which reduce oxygen, which then collapse food webs. An asteroid may strike in a moment, yet the most severe biological losses may follow during months of darkness and years of disruption. The evidence is rarely a simple confession. It is more like a room left after a storm, filled with objects that have shifted from where they once belonged. Tonight, we will read that room carefully. We will notice the missing species, the altered seas, and the chemical fingerprints left behind. And then, with the clues assembled, we will step beyond the cliff and enter the first of 5 vanished worlds. More than 440 million years ago, the continents were arranged in unfamiliar shapes, and almost all complex life still lived beneath the sea. There were no birds in the sky, no grass beneath the wind, and no forests darkening the horizon. The land was mostly bare rock, crossed perhaps by thin microbial crusts and the earliest simple plant close to water. The true abundance of the Ordovician world lay offshore in warm, shallow seas, spread across broad continental shelves. Sunlight filtered through clear water onto communities unlike anything alive today. Brachiopods opened paired shells above the sediment. Trilobites moved across the seabed in many forms, some smooth and small, others armored with spines. Colonies of graptolites drifted in the open water, leaving delicate marks that would later help geologists compare distant rocks. Crinoids lifted feathery arms into the current, while reef-building organisms created shelters for smaller creatures. Above them moved the great predators of the age, straight-shelled nautiloids, relatives of modern squid and octopuses, could grow several meters long. Their chambered shells helped them control buoyancy as they crossed the water in search of prey. Jawless fishes, still modest beside later vertebrates, swam through a world where backboned animals had only begun their long expansion. This interval is remembered for the great Ordovician biodiversification event, when marine life multiplied into new species and ecological roles. Predators became more capable. Burrowing animals disturbed the sediment more deeply. Reefs grew larger and more complex. Food webs developed additional layers, as if the oceans were learning new arrangements. Yet the geography of the planet was quietly preparing a crisis. A vast southern continent, known as Gondwana, drifted across the South Pole. Other land masses lay nearer the equator, surrounded by shallow seas. Because so much life depended upon those warm, sunlit margins, even a modest change in sea level could remove enormous areas of habitat. The atmosphere was different, too. Carbon dioxide remained far higher than today, yet over long spans it began to decline. Weathering rocks and expanding early land plants may have helped draw carbon from the air. At the same time, the arrangement of continents and oceans allowed the southern climate to cool. For millions of years, the Ordovician seas seemed secure. Their reefs widened. Their shells accumulated in pale layers. Creatures fed, reproduced, and disappeared into sediment, unaware that ice was beginning to gather at the far edge of their world. The first great extinction would not arrive as a wall of flame. It would begin with cold, with water withdrawing from the continents, and with the strange sight of a warm planet learning how to freeze. The cooling began far to the south, where Gondwana rested across the pole, and snow survived from one season into the next. Year after year, layer after layer, the snow compressed into ice. Glaciers widened over the land, and enormous volumes of water were drawn out of the oceans. The change was slow enough to escape any single lifetime, yet swift in geological terms. As the ice sheets grew, global sea level fell. Across the tropics, coastlines moved outward. The warm, shallow seas that had covered broad continental shelves became narrower. Reefs and seabed communities were left in shrinking basins or exposed entirely. For creatures adapted to stable tropical water, the loss of habitat was severe. Cooling currents reached farther from the poles, and climate zones shifted toward the equator. This was the first pulse of the end Ordovician extinction. Many groups did not disappear everywhere at once. Their ranges contracted as conditions changed, until populations became isolated in smaller and smaller refuges. Species that could tolerate a wider range of temperature or depth had an advantage. Those tied to particular shallow environments were more vulnerable. Brachiopods, bryozoans, trilobites, corals, and graptolites all suffered major losses. The exact percentages vary depending on how fossils are counted, but the biological turnover was immense. At the level of species, the event ranks among the most severe known in the marine record. The rocks preserve evidence of the cold. Sediments once carried by glaciers remain in parts of North Africa, which then lay near the South Pole. Scratches and deposits reveal moving ice. Changes in oxygen isotopes, measured in fossil material, indicate cooler water and expanded glaciation. Meanwhile, ancient shorelines show that the sea retreated across the continents. And then, almost as important as the cooling, the climate shifted again. The ice began to melt. Sea level rose, flooding the shelves that had recently been exposed. At first, this might sound like relief. Habitats returning, warm water spreading, the crisis reversing. But the recovering oceans were not simply restored to their earlier state. Circulation changed. Nutrient-rich water moved differently through the seas. In many regions, deeper waters lost oxygen. Dark, organic-rich mud accumulated where animals could no longer breathe. So the end Ordovician crisis unfolded in two movements. First came cooling, glaciation, and falling seas. Then came warming, rising water, and widespread oxygen loss. Life was pressed from one direction and then the other. It was not one dramatic instant, but a rapid sequence of planetary adjustments. The first lost world did not end beneath an asteroid. It faded as the boundaries of ocean and climate moved across the globe, quietly redrawing the places where life was able to remain. When the ice retreated and the seas returned, the Ordovician world did not return with them. The water covered the continental shelves again, but many communities that had filled those spaces were gone. Their shells remained beneath new sediment, layered below the extinction boundary, while above it a different collection of organisms began to appear. Recovery started with survivors. Some species had endured in deeper water, warmer regions, or small refugias where conditions remained tolerable. Others survived because they could feed on varied material, reproduce quickly, or tolerate changes in oxygen and temperature. These advantages were not signs of permanent superiority. They were simply useful during this crisis. Once conditions stabilized, the surviving lineages began to spread. Empty habitats offered space, food, and fewer competitors. Brachiopods diversified again. Coral and sponge reefs gradually reformed. Jawless fishes continued to evolve, and later groups of fishes would become increasingly important. The Silurian period saw marine ecosystems regain much of their complexity, though not the exact forms they had lost. This distinction matters. When scientists say that life recovered, they do not mean the vanished species returned. Extinction is irreversible. Recovery means that new ecosystems developed from whatever remained. The process took millions of years, far longer than the extinction itself, and the result was not a repaired Ordovician world, but a new chapter with different dominant creatures. The crisis also revealed something that would recur throughout Earth's history. Ecosystems can appear stable while depending on a narrow range of conditions. The Ordovician oceans were rich because shallow seas were widespread. That same abundance created vulnerability. When sea level fell, the habitat supporting much of that diversity vanished with it. When the climate warmed and oxygen declined, returning water brought a second disturbance instead of rescue. In the fossil record, the event looks like a threshold. Below it is a world expanding into complexity. At the boundary, many branches are cut short. Above it, surviving branches continue, dividing slowly into new forms. The tree of life becomes smaller, then begins to widen again. And while the Silurian seas rebuilt, another transformation was beginning along the continents. Small plants spread farther across damp ground. Roots altered soil and stone. Rivers carried new minerals and nutrients toward the sea. Fishes became larger and more varied, some developing stronger jaws, armor, and fins. Life was beginning to change the planet more actively, and the planet would answer in ways no creature could foresee. The first great extinction had passed. Ahead lay the Devonian, an age of reefs, forests, armored fishes, and a crisis that would not arrive in two clear pulses, but in disturbances repeated across millions of years. The Devonian opened upon a world that was becoming more adventurous. In the oceans, fishes were no longer small, tentative experiments. They had diversified into hunters, grazers, scavengers, and armored giants. Some carried heavy plates across the head and chest, giving them the appearance of fortresses. Others had developed powerful jaws, stronger fins, and bodies shaped for speed. Among them were early sharks, lobe-finned fishes, and the ancestors of lineages that would one day move on to land. The seas were rich with life. Vast reef systems stretched across warm, shallow waters built by corals, sponges, and other organisms that created complex habitats. Ammonoid relatives appeared, coiling their shells into elegant spirals. Trilobites still crossed the seabed, though their long history was already narrowing. On land, the transformation was quieter, but just as profound. At the beginning of the Devonian, most vegetation remained low to the ground. Small plants clustered near rivers and damp soils. By the period's later stages, true forests had emerged. Trees grew taller, roots reached deeper, and broad canopies began to shade the earth beneath them. These forests did more than change the view. Roots broke rock into soil. Fallen leaves and decaying wood added organic material to the land. Rivers carried that material toward lakes and seas. Plants drew carbon dioxide from the atmosphere, using sunlight to build stems, branches, and roots, while releasing oxygen. The planet was being altered by life itself. Along muddy shorelines, certain fishes possessed thick, muscular fins supported by bones. In shallow pools where oxygen could become scarce, the ability to lift the body, breathe air, or push across wet ground offered an advantage. Over immense spans of time, some descendants of these fishes would give rise to the first four-limbed vertebrates. Nothing about this change was sudden. There was no single day when a fish became an animal of the land. Generations accumulated small differences, and environments rewarded some of them. Fins became more capable of bearing weight. Skulls changed. Lungs and limbs took on new importance. The Devonian is often called the age of fishes, but it was also the age when life began to knit land and sea together more tightly than ever before. And that new connection carried consequences. The forests were stabilizing soils, changing rivers, and drawing gases from the atmosphere. Nutrients once locked in stone were being loosened and carried toward the oceans. In the beginning, these changes may have encouraged growth, but abundance can create imbalance. As the Devonian world became greener and more complex, its oceans began to show signs of stress. In dark layers of ancient rock, scientists would later find the evidence. Seas that had lost their oxygen, reefs that had stopped growing, and communities that vanished not in a single blow, but in waves. The first forests did not know they were changing the atmosphere. Their roots simply followed moisture downward. Their leaves opened toward the light. Their fallen branches settled into soil, and each season added another thin layer of organic matter to the land. Yet, across millions of years, these ordinary acts became planetary forces. When roots penetrated rock, they accelerated weathering. Minerals were broken apart and carried by rain into streams and rivers. Phosphorus and other nutrients entered lakes and coastal seas, where they encouraged algae and microscopic organisms to grow. At first, greater productivity could support richer food webs, but when large blooms died, bacteria consumed the sinking organic matter. In doing so, they used oxygen dissolved in the water. If circulation failed to replace it quickly enough, deeper seas became depleted, then nearly lifeless. This process is familiar today in smaller settings, where nutrient-rich runoff can create coastal dead zones. In the Devonian, it may have occurred across far broader regions. The expanding forests may also have helped reduce atmospheric carbon dioxide. Weathering removes carbon from the air, and plants store it in living tissue and soil. Lower carbon dioxide can cool the climate, especially when several processes work together. So the same vegetation that made the continents more habitable may have contributed to instability in the oceans. Scientists remain cautious. The late Devonian extinction was not caused by one simple mechanism, and the evidence differs between regions. Changes in sea level repeatedly altered shallow habitats. Climate moved between warmer and cooler states. Researchers have also examined changes in ocean circulation. The clues point not to one clean catastrophe, but to a planet under repeated pressure. In the rocks, the most important evidence often appears as dark, organic-rich shale. These layers formed where oxygen was scarce and decay was incomplete. Fossils above and below them reveal sudden losses among reef builders, trilobites, brachiopods, and many kinds of fish. Some of the largest reef systems Earth had yet produced collapsed and did not return in the same form. Armored placoderms, once among the dominant vertebrates in the sea, suffered heavily during later pulses of the crisis. The forests, meanwhile, continued their slow expansion. This gives the Devonian extinction an unusual character. Life on land was advancing while life in the oceans was being disrupted. One ecosystem success may have helped destabilize another. It was not intention, and it was not failure. It was consequence. Earth is a connected system. Air moves into water. Rivers carry the land toward the sea. Living things reshape chemistry simply by feeding, growing, and dying. By the late Devonian, those connections had become powerful enough to unsettle the balance of an entire world. The late Devonian extinction did not arrive on one recognizable day. Instead, the crisis unfolded across several million years in repeated episodes of environmental change. To scientists, this makes the Devonian both fascinating and difficult. Two intervals stand out. The first is known as the Kellwasser event, near the end of the Frasnian stage. The second, several million years later, is called the Hagenberg event. Other disturbances affected different regions and groups. The seas repeatedly lost oxygen. In many places, dark shales spread across the seabed, preserving organic carbon that had not fully decayed. Reefs declined. Species adapted to warm, shallow marine environments disappeared. Some survivors endured one pulse only to vanish during another. Placoderm fishes offer a clear example. These armored vertebrates had occupied many ecological roles. Some were small bottom feeders. Others were immense predators, equipped with sharpened plates instead of true teeth. By the end of the Devonian, their long experiment was over. Their disappearance did not mean that fishes themselves failed. Sharks, ray-finned fishes, and lobe-finned fishes persisted, and their descendants would inherit the oceans. But the balance of power changed. The reefs suffered a similar transformation. Devonian reef systems had been among the largest yet seen on Earth, but many reef-building groups declined severely. After the extinction, reefs remained limited for a long interval. Empty ecological space did not fill at once. On land, early forests continued to spread, while four-limbed vertebrates became more established in wetlands and river systems. The crisis therefore selected unevenly. It was severe, but not universal, and its effects varied by habitat. Why did it last so long? One possibility is that several causes reinforced one another. Volcanism may have altered climate and ocean chemistry. Expanding forests may have increased weathering and nutrient runoff. Cooling episodes may have lowered sea level, while later warming reduced oxygen in the oceans. Each change made ecosystems less resilient to the next. This is a pattern we will encounter again. Mass extinction does not always require one overwhelming blow. Sometimes it emerges from stresses arriving faster than ecosystems can adjust. The Devonian world did not collapse into silence. It thinned. Reefs became smaller. Food webs simplified. Certain dominant groups disappeared while others passed through the crisis almost unnoticed. In the long aftermath, survivors reorganized the living world. Amphibian-like vertebrates expanded through wetlands. Seed-bearing plants appeared. Reptile ancestors emerged from early land animal lineages. The age of fishes was ending, but another age was gathering far inland on continents slowly moving toward one another. By the beginning of the Permian period, Earth's continents were assembling into one enormous landmass. It was called Pangaea, and it stretched across much of the planet, surrounded by a global ocean known as Pangaea. Seas reached into its margins, but the interior lay far from the moderating influence of water. The result was a world of extremes. Along the coasts, seasonal rains could support forests and wetlands. Deep inland, dry regions expanded beneath intense summers and cold winters. Winds crossed distances difficult to imagine, lifting dust from plains that had no modern equivalent. The animals of Pangaea were not dinosaurs. Those would come later. The dominant large land vertebrates included synapsids, the evolutionary group that would eventually produce mammals. Some carried sails along their backs. Others had heavy bodies, tusks, beaks, or powerful jaws. Among them were herbivores adapted to tough vegetation and predators capable of crossing wide territories. One of the most successful survivors of the later crisis would be Lystrosaurus, a stout, tusked plant eater whose fossils have been found across regions now separated by oceans. Its distribution would help later scientists recognize that the continents had once been joined. The Permian seas were equally strange. Reefs flourished in warm waters. Brachiopods remained abundant. Ammonoid relatives moved through the open ocean, while sharks and bony fishes occupied a growing variety of niches. Trilobites, already ancient by then, still survived on the seabed. Life had recovered from the Devonian disruptions and diversified again. Yet Pangaea's vastness created vulnerability. Its interior climates were severe, and its coastlines were proportionally shorter than those of several separated continents. Many marine organisms depended on continental shelves where sunlight and nutrients supported abundant life. Changes in sea level or ocean chemistry could therefore affect a large share of available habitat. Deep beneath the northern part of the supercontinent, another process was beginning. In the region that would one day become Siberia, magma rose through cracks in the crust. It spread underground, heated surrounding rocks, and eventually reached the surface. The eruptions did not resemble one isolated volcano. They occurred across an immense area, building layer after layer of basalt. Such regions are known as large igneous provinces. The Siberian traps would become one of the largest examples in Earth's history. For a time, the Permian world continued as before. Animals crossed dry floodplains. Trees released pollen into seasonal winds. Shells accumulated on the seabed. Rivers carried sediment from Pangaea's interior toward the sea. But the eruptions were gathering force. Soon, the atmosphere would begin to change. The oceans would warm, and the most severe extinction in the history of complex life would begin. The first eruptions in Siberia may have seemed local, though their true scale was immense. Fissures opened across the crust, and molten rock poured outward in broad sheets. Unlike a steep volcanic cone erupting once and falling quiet, these flows accumulated repeatedly, covering landscapes beneath dark basalt. The eruptions continued in pulses over thousands of years, then longer. Magma moved through underground layers rich in coal, organic matter, salts, and other carbon-bearing sediments. The heat transformed those rocks and released additional gases, including carbon dioxide and methane. The atmosphere began to hold more heat. Carbon dioxide does not warm a planet instantly, but it alters the balance between incoming sunlight and outgoing heat. As concentrations rose, global temperatures climbed. The change was rapid compared with the pace at which many species could migrate or evolve. Sulfur gases complicated the picture. In the short term, they could reflect sunlight and cool the surface. Acid rain may have damaged soils and vegetation, but carbon dioxide remained much longer, pushing the climate toward sustained warming. The oceans absorbed part of that carbon. As carbon dioxide dissolved in seawater, it formed carbonic acid and shifted the chemistry on which shell-building organisms depended. At the same time, warmer water held less oxygen. Ocean circulation weakened, and oxygen-poor zones expanded through deeper waters and onto continental shelves. Some microorganisms thrived in those altered conditions. Others produced toxic compounds. Food webs became unstable from the bottom upward. On land, heat and drought stressed forests. Wildfires became more common in some regions. Soils eroded when vegetation declined, carrying sediment into rivers and coastal seas. Each system disturbed another. Scientists reconstruct this chain through many forms of evidence. They study mercury preserved in sediments as a possible signal of volcanism. They measure abrupt changes in carbon isotopes, indicating a large addition of light carbon to the atmosphere and oceans. They date volcanic rocks and extinction boundaries, finding that the most intense losses closely overlapped major eruptive phases. The scale is difficult to hold in the mind. The Siberian traps eventually covered millions of square kilometers, though later erosion and burial concealed much of the original province. The eruptions released enough material to alter climate far beyond the horizon of any creature living nearby. This was not merely a volcanic disaster. It was a cascade: eruption, gas release, warming, acidification, oxygen loss, habitat collapse. The Permian world had endured droughts, changing seas, and earlier extinctions. But now, several stresses were arriving together, each magnifying the next. The greatest biological crisis Earth had yet experienced was no longer approaching. It had begun. The collapse spread through the oceans first, though no coastline could contain it. As temperatures rose, tropical waters became too warm for many marine animals to tolerate. Warm water carried less dissolved oxygen, and circulation weakened as the contrast between surface and deep water diminished. In many basins, oxygen-poor zones expanded upward from the depths, pressing life into a narrowing band near the surface. For creatures that breathed through gills, the change was relentless. Metabolism accelerated in the heat, increasing the need for oxygen at the very moment oxygen became harder to find. Large, active animals were especially vulnerable. Reef builders struggled as seawater chemistry shifted. Shell-forming organisms faced more acidic conditions. Food webs weakened from the base, then failed through every level above. The pattern was not identical everywhere. Some high-latitude regions remained cooler for longer, while shallow tropical seas became biological traps. Yet the losses were global. By the end of the crisis, the final trilobites had vanished after nearly 300 million years on Earth. Many brachiopods, corals, and other marine groups disappeared or were reduced to a few surviving lineages. On land, forests collapsed across wide regions, and many large synapsids and amphibians were lost. The event became known as the Great Dying. Estimates differ because the fossil record is incomplete, but it was the most severe extinction known among complex life. The majority of marine species disappeared, and land ecosystems were transformed almost beyond recognition. The rocks preserve the sequence. A sudden change in carbon isotopes appears across many regions, recording a vast disturbance to the carbon cycle. Fossil pollen and charcoal reveal damaged vegetation and fire. Layers once formed in oxygenated seas give way to dark sediments deposited under stagnant water. In some places, minerals suggest that hydrogen sulfide, produced by microbes in oxygen-free conditions, may have reached sunlit waters. The crisis was not one single mechanism. It was several systems failing together. Volcanism changed the atmosphere. Warming altered circulation. Oxygen loss spread through the sea. Acidification weakened shell builders. On land, heat, drought, fire, and erosion stripped ecosystems of stability. Each pressure made the next one more difficult to survive. And yet life did not vanish entirely. Small pockets endured in cooler waters, sheltered basins, river valleys, and regions less exposed to the worst conditions. Some species survived because they were small, others because they could eat almost anything, reproduce quickly, burrow, migrate, or tolerate poor oxygen. The world was devastated, but not empty. In the silence after the Great Dying, those survivors remained scattered and unremarkable, carrying the future within them. The first years after the Great Dying did not bring a quick return to abundance. The eruptions continued in pulses. Carbon remained high in the atmosphere, temperatures stayed elevated, and the oceans repeatedly slipped back toward low oxygen conditions. Even when a species managed to expand, another wave of heat or chemical change could reduce it again. Recovery became a story of interruption. In the earliest Triassic seas, ecosystems were unusually simple. A few hardy organisms spread across enormous areas. creating what paleontologists sometimes call disaster communities. Certain bivalves appeared in great numbers, not because the world was healthy, but because they could tolerate conditions that excluded more specialized competitors. On land, one animal became especially common. Lystrosaurus was a barrel-bodied herbivore with a short face and two tusks. It was not graceful, enormous, or especially well-armed. Yet it possessed qualities that may have helped it through the crisis: a sturdy build, a broad diet, and perhaps the ability to burrow or survive seasonal hardship. Its fossils are abundant in rocks from Africa, India, Antarctica, and other parts of former Pangaea. For a time, it may have represented a striking share of the large land vertebrates alive in some regions. This abundance was not a sign of flourishing diversity. Forests also returned unevenly. In several places, the fossil record shows a prolonged interval with little coal formation, suggesting that stable, dense forests were rare. Instead, low vegetation, ferns, and opportunistic plants occupied disturbed ground. Rivers changed course more often where roots no longer held the soil firmly in place. Complex reefs remained absent for millions of years. The time required for recovery reminds us that an extinction boundary is not a single line between death and renewal. The line is followed by a long corridor. Ecological roles must be rebuilt. Predators require prey. Reef dwellers require reefs. Forest animals require soils, shade, and vegetation that may take generations to establish. Evolution also needs time. Surviving lineages diversify through small inherited differences accumulated across countless births. Empty habitats create opportunity, but opportunity does not instantly produce complexity. For much of the early Triassic, Earth remained unstable, hot, and biologically sparse. Then, gradually, the carbon cycle steadied. Oceans regained more oxygen. Vegetation returned across the continents. New groups began to spread. The recovery was not a restoration of the Permian. It was the construction of another world. From the few branches that remained, reptiles diversified, marine ecosystems became richer, and new forms appeared that no Permian animal had known. Among them were the earliest dinosaurs, still small and easily overlooked, walking into a world that had not yet decided what they would become. The Triassic world began as a landscape of survivors, but it slowly became a laboratory of new forms. Pangaea still joined nearly all the continents together. Its interior remained dry and strongly seasonal, while monsoon rains affected the coasts. Across this immense landmass, animals could spread over distances that would later be divided by oceans. Reptiles diversified with remarkable speed. Some returned to the sea, developing paddle-like limbs and streamlined bodies. Others took to the air on membranes stretched over elongated fingers. On land, crocodile-lined archosaurs appeared in many shapes: lightly built runners, heavy armored herbivores, and large predators with upright limbs. The first dinosaurs lived among them. They were not yet the unquestioned rulers of the continents. Many were small, two-legged animals, quick on their feet and modest beside the larger archosaurs around them. Early forms such as Aeraptor and Herrerasaurus appeared in the late Triassic of what is now South America. Other dinosaur lineages soon spread across Pangaea. Their posture mattered. Unlike sprawling reptiles, dinosaurs carried their limbs more directly beneath the body. This arrangement could support efficient movement over long distances. Their skeletons also became lighter in some lineages, while air sac systems related to those of modern birds may have improved breathing. Yet none of these advantages guaranteed success. For tens of millions of years, dinosaurs shared the world with rivals that were just as widespread and, in many habitats, more dominant. Large amphibians waded in rivers. Crocodile relatives hunted on land. Herbivorous reptiles occupied the plains. The future remained open. Meanwhile, the planet itself was beginning to change shape. Deep beneath central Pangaea, the crust stretched and thinned. Faults opened across regions that would one day become the margins of North America, South America, Europe, and Africa. Valleys formed along the growing fractures. Lakes filled some of them, leaving sediments that still preserve footprints, fish, pollen, and volcanic ash. These were the first stages in the breakup of the supercontinent. As the crust weakened, magma rose through the fractures. The process would eventually create the Atlantic Ocean, but before any broad sea appeared, it produced one of the largest volcanic provinces in Earth's history. The Central Atlantic Magmatic Province spread across millions of square kilometers. Basalt erupted in repeated pulses through landscapes separated today by thousands of kilometers. The Triassic ecosystems continued around it. Dinosaurs crossed floodplains. Early mammals, still small and nocturnal, moved beneath vegetation. Conifers released pollen into warm air. Then the carbon cycle shifted sharply. The eruptions were no longer only rearranging continents. They were beginning to rearrange life. The end Triassic crisis began with fire rising from the seams of a breaking world. Across central Pangaea, lava flowed from long fissures rather than a single volcanic mountain. Each eruptive pulse covered broad areas with basalt. More important than the rock itself were the gases released as magma reached the surface and heated surrounding sediments. Carbon dioxide entered the atmosphere in enormous quantities. Temperatures climbed. The oceans absorbed part of the added carbon, becoming more acidic. Marine organisms that built shells or skeletons from calcium carbonate faced increasing difficulty, while changing circulation encouraged oxygen-poor conditions in some basins. The carbon isotope record shows several abrupt disturbances near the extinction boundary, suggesting repeated injections of carbon rather than one continuous release. Volcanic layers found on different continents can be matched in age to the biological losses, tying the breakup of Pangaea to the crisis with growing precision. On land, the climate became increasingly unstable. Intense warming could be followed by shorter intervals of cooling when sulfur aerosols reflected sunlight. Rainfall patterns shifted across the supercontinent. Forests changed, soils eroded, and habitats moved faster than many species could follow. Large amphibians declined sharply. Several major groups of crocodile-lined archosaurs disappeared. Many marine reptiles, ammonoids, reef organisms, and planktonic species were also lost. Once again, the extinction was selective. Some animals were trapped by specialized diets or narrow habitats. Others may have been unable to regulate body temperature through sudden climate swings. Organisms with wide geographic ranges, flexible feeding strategies, or rapid reproduction had better odds. The dinosaurs survived. Scientists still debate exactly why. Their upright posture and efficient respiratory systems may have helped. Some early dinosaurs may have tolerated cooler conditions at high latitudes, giving them resilience during volcanic winters. Small body size and broad distribution likely mattered as well. But survival was not victory in the moment. It was simply persistence while competitors disappeared. The event occurred around 201 million years ago, marking the boundary between the Triassic and Jurassic periods. In the rocks, pollen assemblages change. Fossil communities simplify. Volcanic basalt appears beside sediments, recording abrupt warming and ocean disturbance. Then, above the boundary, dinosaur fossils become more widespread and varied. The extinction had removed many groups that once occupied the same ecological roles. Predatory niches, herbivorous niches, and entire landscapes were suddenly open. The breakup of Pangaea had created a biological doorway. Dinosaurs did not force it open alone. They were among the creatures still standing when the old world fell away. The Jurassic began with opportunities spread across a wounded planet. Where large competitors had vanished, surviving dinosaurs expanded. Some lineages became enormous, walking on four pillar-like legs beneath long necks and balancing tails. Others remained light and quick, hunting in forests and across open floodplains. Armored forms appeared, and the earliest feathered dinosaurs moved through branches or along the ground. Over time, dinosaurs occupied nearly every major terrestrial role available to large vertebrates. Sauropods browsed high vegetation in herds. Theropods became the dominant large predators. Smaller plant eaters fed close to the ground. Their success lasted not for a brief age, but for more than 130 million years after the end Triassic extinction. The continents slowly separated. The Atlantic widened from narrow rift valleys into an ocean. Coastlines lengthened, shallow seas spread, and isolated populations evolved along different paths. The climate was generally warm, with little permanent polar ice for much of the Mesozoic. Life in the oceans was equally rich. Ichthyosaurs and plesiosaurs hunted beneath the waves. Ammonites diversified into many coiled forms. Reefs returned. Planktonic organisms built tiny shells that later became layers of chalk. In the sky, pterosaurs crossed coastlines and inland seas. Birds evolved from small feathered dinosaurs, carrying one dinosaur lineage into the air. and eventually through the extinction still to come. By the Cretaceous, flowering plants were transforming the continents. Their blossoms, fruits, and leaves created new relationships with insects. Bees evolved from wasp-like ancestors. Forests became increasingly familiar in structure, though they remained filled with animals that have no modern counterpart. This world was not waiting to end. It was mature, productive, and deeply established. Near the close of the Cretaceous, enormous titanosaurs crossed southern landscapes. Horned dinosaurs and duck-billed herds moved through North America. Tyrannosaurs hunted at the top of food webs. Small mammals lived in burrows, trees, and the shadows of larger creatures. Far beyond Earth, an asteroid followed an orbit shaped by gravity. It was roughly 10 kilometers across. Against the scale of a planet, it was small. Against the scale of a city, it was immense. For millions of years, its path had no meaning to life below. Then, 66 million years ago, the paths of Earth and asteroid intersected. The object approached at many kilometers per second, carrying energy far beyond any ordinary volcanic eruption. Beneath it lay a shallow tropical sea, near what is now the Yucatan Peninsula. The Cretaceous morning began like countless mornings before it. Sunlight reached the forests. Insects moved among flowers. Waves crossed the coast. Above them, almost silently, the final great extinction was arriving. The asteroid entered Earth's atmosphere faster than sound could travel ahead of it. For a few seconds, the sky over the shallow sea of the Yucatan brightened beyond daylight. The object did not slow in any meaningful way. It struck at roughly 20 kilometers per second, releasing energy measured not in ordinary explosions, but in millions of times the force of the largest human-made weapons. Rock at the impact point was compressed, melted, and vaporized. A crater nearly 200 kilometers wide began to form beneath the sea and coastal limestone. The ground moved outward in waves. Earthquakes crossed continents. Water was thrown from the seafloor, and enormous waves spread through nearby oceans. But the local destruction, vast as it was only the beginning. Material blasted from the crater rose through the atmosphere and traveled around the planet. Tiny droplets of molten rock cooled into glassy spheres before falling back to Earth. Some re-entering debris heated the upper atmosphere, and wildfires may have ignited across broad regions. Dust, soot, and sulfur-rich aerosols gathered overhead. The sunlight weakened. For plants and plankton, this was the central disaster. Photosynthesis depends on light, and when light faded, the base of many food webs began to fail. On land, leaves withered and fresh growth slowed. In the oceans, microscopic plankton declined, and the creatures that fed upon them lost their food in turn. The impact site made the crisis worse. The asteroid struck rocks rich in sulfur and carbonates. Vaporized sulfur compounds reached the atmosphere, where they formed aerosols capable of reflecting sunlight and cooling the surface. Temperatures fell rapidly in what scientists call an impact winter. The darkness did not need to last for centuries to transform the world. Months of reduced light, followed by years of unstable climate, were enough to place severe pressure on ecosystems already built around regular sunlight and seasonal growth. The evidence rests in a narrow layer found across the globe. It contains unusually high concentrations of iridium, an element rare in Earth's crust, but more common in asteroids. It also contains shocked quartz, grains altered under immense pressure, and tiny glassy particles created during impact. Beneath the Gulf of Mexico lies the buried Chicxulub crater, matching the age of the boundary where so many fossils disappear. For decades, scientists debated whether volcanism, impact, or some combination caused the extinction. Vast eruptions were already occurring in India, forming the Deccan Traps. Those eruptions affected climate before and after the collision, yet the timing and global signature of Chicxulub leave little doubt about the decisive blow. The world of the Cretaceous had survived volcanic change before. This time, the sky itself went dark. In the first hours after the impact, distance offered little protection. Shock waves moved through the crust. Tsunamis crossed seas. Debris fell far beyond the crater. Yet for most organisms, the greatest danger was not the collision itself, but the long disruption that followed. Daylight became dim and uncertain. As dust and sulfur aerosols spread, the planet cooled. Rain carried acids from the atmosphere. Forests burned in some regions, while in others they simply failed beneath the darker sky. Rivers filled with ash and soil. Plants died first in many food chains. Large herbivorous dinosaurs required enormous quantities of vegetation. When leaves and new growth became scarce, their numbers fell. Predators depended upon those herbivores and declined with them. A food web that had taken millions of years to assemble began to unravel from the bottom upward. In the sea, the pattern was similar. Photosynthetic plankton suffered when light was blocked. Ammonites, ancient survivors with coiled shells, disappeared. Many marine reptiles vanished. Reef communities declined as the chemistry and productivity of surface waters changed. The losses were severe, but not evenly distributed. Every non-avian dinosaur disappeared, yet birds survived. Crocodilians endured. Turtles, amphibians, fishes, insects, fungi, and small mammals passed through the boundary. Chance mattered, but so did lifestyle. Size was important. Small animals needed less food and could reproduce more quickly. Creatures that burrowed or sheltered in water were protected from heat, fire, and temperature swings. Flexible diets offered another advantage. An animal that could eat seeds, insects, carrion, roots, or decaying material had more options than one dependent on fresh leaves or a single prey species. Seeds were especially valuable. They could remain dormant through darkness and cold. Fungi and detritus-feeding organisms could live on the immense quantity of dead material left behind. In rivers and lakes, food chains based partly on decay may have remained more stable than those relying immediately on sunlight. Birds survived, but only a few lineages did. Many Cretaceous birds lived in trees and vanished when forests collapsed. Ground-dwelling forms may have had better odds. Living birds descend from those survivors, meaning dinosaurs did not disappear completely. They still move through gardens, coasts, deserts, and city skies. The boundary between Cretaceous and Paleogene is therefore not only a grave, it is also a filter. On one side stand ecosystems dominated by giant reptiles. On the other remain smaller bodies, buried seeds, patient eggs, and animals able to live for a time on what the old world left behind. The future belonged not to the strongest creatures, but to those whose needs could shrink with the world. When sunlight returned more reliably, the surviving world was sparse. Forests did not reappear all at once. In many places, the earliest recovery is marked by a sudden abundance of fern spores. Ferns spread quickly across disturbed ground. This brief fern spike is preserved above the boundary, a green signature of land beginning again. Then came shrubs, trees, and more complex plant communities across the recovering world. As vegetation recovered, insects diversified with it. Birds expanded into new habitats. Mammals, which had lived for millions of years beneath the dominance of dinosaurs, began to occupy ecological spaces that had suddenly opened. Early Paleogene mammals were not yet whales, horses, elephants, or familiar primates. Many were small and generalized, but their descendants diversified rapidly into runners, climbers, swimmers, and specialized feeders. The disappearance of the non-avian dinosaurs did not cause mammals to appear. Mammals were already ancient by then. What changed was opportunity. Competition had fallen. Forests, plains, rivers, and coasts contained empty roles. Evolution reshaped the surviving lineages until a new world emerged. This pattern appears after every great extinction. The Ordovician crisis removed many marine species, and later seas, filled with different fishes and reef builders. The Devonian losses ended the dominance of armored placoderms. The Permian catastrophe erased entire ecosystems, after which archosaurs and eventually dinosaurs expanded. The end Triassic removed major dinosaur rivals. The end Cretaceous opened pathways for mammals and modern birds. Yet renewal should not be mistaken for recovery in the ordinary sense. The old worlds never returned. No later animal recreated a trilobite. Permian reefs were not rebuilt by the same organisms. Ammonites did not return. Extinction removes histories that cannot be repeated. New diversity can arise, but it requires time. After the end Permian extinction, complex ecosystems took many millions of years to stabilize. After Chicxulub, some food webs recovered more quickly, but biodiversity remained diminished for a long interval. The empty space after catastrophe is crossed slowly by survivors, and survival itself is only the first step. A lineage must find food, reproduce, adapt, and endure. Its descendants must divide into new species and habitats. In rock, that widening represents countless ordinary lives continuing through uncertainty. From those lives came the Paleocene forests. From those forests came new mammals, new birds, and eventually the distant branches that would lead to us. Not because history aimed in our direction, but because a few small creatures remained when the larger world disappeared. Seen together, the 5 extinctions resemble separate mysteries with recurring clues. The end Ordovician began with cooling ice and falling seas. The late Devonian unfolded in pulses linked to oxygen-poor oceans, climate shifts, nutrients, and perhaps volcanism. The end Permian and end Triassic were tied to immense volcanic provinces and rapid carbon release. The end Cretaceous was struck by an asteroid. The triggers differed greatly indeed. The consequences often converged, revealing the same vulnerabilities beneath very different disasters. Rapid climate change pushed organisms beyond familiar conditions. Sea levels shifted, shallow habitats vanished, warmer oceans held less oxygen, and excess carbon changed seawater chemistry. Food chains weakened as disturbances spread through the Earth system. Mass extinction is rarely only about death arriving faster. It is also about recovery becoming harder. A species may survive heat, but lose its food. It may tolerate acidic water, but fail when oxygen declines. It may escape a local disaster, only to discover that its breeding grounds have disappeared. Several moderate pressures can become catastrophic when they arrive together. This is why scientists study the Big Five so closely today. They rid fossils, compare ancient carbon changes, and model heat moving through oceans and air. The past is no perfect duplicate of the present, but it reveals how living systems respond when change becomes rapid and widespread. Many researchers now ask whether Earth is entering a 6th mass extinction. The phrase must be used carefully. The 5 ancient events are defined across millions of years. The present is still unfolding, and estimates vary by organism and period. What is clear is that extinction rates for many studied groups are elevated above long-term background levels. Habitat loss, overharvesting, invasive species, pollution, and human-driven climate change are placing pressure on populations across land and sea. Unlike an asteroid or volcanic province, the principal cause is the activity of one species that can understand the evidence. That difference matters. Humans are not outside nature observing a distant crisis. We are participants within the same atmosphere, oceans, soils, and food webs. Yet our ability to study the past also gives us an unusual ability to respond. Protected habitats can help populations recover. Hunting limits, restoration, and lower emissions cannot guarantee success everywhere. But they show that decline is not always irreversible. The rocks teach that extinction is permanent. They also teach that causes leave traces. Patterns can be recognized, and choices made before a boundary are different from regrets made after it. The geologist's hand returns to the narrow line in the cliff. Night has settled over the exposed stone. The layers are cooler now, their colors softened beneath the moon. Somewhere within them lie the remains of seas that vanished, forests that burned or withered, and animals that once seemed as permanent as mountains. The line is thin because geology compresses experience. 1,000 years can become a grain of sediment. 1,000,000 can fit within the width of a hand. Entire evolutionary radiations appear as bands of shell and bone, followed by abrupt silence. Yet above every extinction boundary, the rock continues. This is the deepest pattern in the story. Life endured Ordovician ice, Devonian disruption, the volcanic heat of the Great Dying, the breakup of Pangaea, and the darkness after Chicxulub. But life did not endure as an unchanging whole. It survived through particular bodies: a fish in tolerable water, a reptile in a sheltered valley, a seed beneath the soil, a mammal inside a burrow, a bird that could feed on what remained. The grand continuity of life was carried by small, local acts of persistence. Every living species descends from such survivors. Birds continue one dinosaur branch that crossed the final boundary. Mammals carry lineages that stayed small through the age of giants. Fishes, insects, fungi, and plants also carry the record of crises passed one generation at a time. We do too. The atoms in our bodies were forged in stars, gathered into Earth, and cycled through oceans, rocks, air, and earlier life. The branches leading toward us were nearly interrupted more than once. Their survival was not inevitable, and neither was the world we know. Had one extinction unfolded differently, another group might have flourished, and forests or seas might now contain forms beyond our imagining. Earth's history is not a staircase leading upward. It is a branching path, repeatedly narrowed by catastrophe and widened again by time. There is humility in that knowledge. Our species occupies only a brief layer near the top of the cliff. We arrived late, carrying the inheritance of worlds we never saw. The rocks do not promise that life will always remain familiar, nor that recovery will be quick. They offer something quieter. They show that endings and beginnings are often pressed close together. Survival may belong to the small, adaptable, and overlooked. The living world is not a permanent background, but a rare continuity entrusted for a little while to the present. The wind moves softly and steadily across the cliff. The ancient seas are still. Above them, the newest layer waits beneath the patient stars, unfinished and open. The world slows gently, and so do we. Good night.